Hello everyone, welcome to another video on shell coding on ARM Assembly Linux 32-bit course presented on YouTube. So in this one we are going to talk about the stack instructions which we can use in our ARM program. So talking about the stack, what is a stack? So a stack is a last in first out data structure which is used to store some data. What I can say about the stack, it is a container which is used to store some data one at a time, and the data which we store have some significance, have some speciality. And the speciality is that whatever data we store in the stack, the end data or the last data which we have inserted into the stack will be popped out first. So let me just demonstrate you it via a slide. So think of a stack like a simple container which is used to some data. So we are just injecting or inserting data 1, then 2, then 3. So by the knowledge gained from the previous slide, we can easily say that the data inserted at the very last or the latest data we inserted into the stack will be popped out first or removed first. So it happens actually the same. So the data which is inserted at the very end is popped out first. Then the 2 will be popped out, and then 1 will be popped out. So we can easily say another way, like the data which we have inserted first will be removed at the last, or the converse, the data we have inserted at the very last will be popped out first. Both actually means the same. So this is how the stack works. So I have just demonstrated a simple screenshot of a debugger session where the push instruction is used and the pop instruction is used, which is used to just push some data, which is the registers actually, to the stack and pop some registers from the stack. So how does the push and pop instructions actually work in a program layout? Many of you may have a question like, where does a stack reside? So a stack resides in every program layout. Every process which you have used or which you are using in your program have their own separate stack, have their own separate stack layout. So a stack always resides in the higher memory addresses of a particular process, which is just identified by the base pointer, which stores the base address from where the stack starts. And a main thing which we may need to notice is that the stack always grow from higher memory address towards the lower memory address. And what does the stack pointer or the R13 register stores is the top of the stack. So R13 register will always store top of the stack, and R11 register will always store the base address of the stack. So whenever a stack grows, we can easily conclude that the R13 register or the top of the stack is decrementing, because it is growing from higher memory address towards a lower memory address. And from this perspective, if anybody sees the stack, the R13 register will decrement because stack is growing. So let us just execute a simple stack instruction, which is the push instruction, where we are pushing data of R1 and data of R2, and the register set is described inside these curly braces. So what the data in R1 and R2 is stored is 1, 2, 3, 4 and 5, 6, 7, 8. So whenever we execute this push instruction, what happens here is the data at the very end or the R2 register is pushed first. So data on the stack will be 5, 6, 7, 8, which is actually the data on the or in the R2 register. Then the R1 register will be pushed on the stack, which is actually 1, 2, 3, 4. So by this, the stack pointer will point to the top of the stack, pointing towards the data where we have stored 1, 2, 3, 4 and 5, 6, 7, 8. So at this point, if you want to just execute another stack instruction or the pop instruction, what we can easily say is that we want to push data of the top of the stack into the R5 register and the R6 register. It is just an example which I am demonstrating you. So after executing this particular instruction, what is happening here actually is the data top of the stack or the data in the R1 register, which is actually the 1, 2, 3, 4, will be moved or popped in the R5 register, and the stack pointer will point to the R2 register. Stack pointer always increments or decrements, or we can say changes, with every push or pop instruction. so stack pointer is always fluctuating. So after the first pop operation into the R5 register, the stack pointer will point to the data of the R2 register, which is actually the 5678. So after another pop into the R6, what happened here is the data 5678 will be popped into the R6 register and the stack will be empty again. So the stack pointer will point to the exact address where the base pointer is pointing, or we can say stack pointer and base pointer is actually the same, or the stack is empty. So after these operations, what we can say is we have moved data from R1 and R2 register to the R5 and R6 register with a single instruction. What we have just minimized is multiple move operations like moving again R5 with R1 and moving R6 with R1. So we have just decremented or minimized the usages of move instruction with the help of push instruction. So there are multiple ways by which we can use push in and pop instructions. So these doesn't vary. It is beyond your limitations how we can use or utilize the stack. So there are some limitations which we may need to notice about while using the stack instructions in ARM is that we can only use registers as the operands. We cannot use immediate value. So based on the prior slides which we have just noticed, we are not pushing any kind of immediate value. We are only pushing registers like the R1 and link register and not any kind of immediate value. So doing so will yell out an error because immediate value pushing on the stack is invalid. So don't do that. Also another limitation is that the register which we will specify in the register set must be in ascending order. What I mean is that we have to push R1, then R2, then R3. So it will be valid. What we cannot do is like pushing R5 or R7, then R5, then R0. So the registers are not in any kind of order, in ascending order. So this would be invalid. So assembler will yell out an error. So prevent doing this because it is invalid. Another limitation which we are going to see while using the stack instructions is we cannot use the exact same register in a single stack instruction. Suppose you want to push a same value onto the stack 2 or 3 times. So what you might do mistakenly is push the data R0, then R0, then R0 to push the exact same data onto the stack. So don't do that, it is invalid. Assembler will yell out an error because by the assembler it is easily specified that you cannot use the same register again and again in a single stack instruction. What you can do is move the same value in multiple registers like the R0, then R1 and R2. Then you can just push R0, R1 and R2. That would be a valid. So don't try to do these 3 things because these are invalid. Another thing which I need to just mention you is if you want to specify multiple registers like R1, R2, R3, R4, R5, R6, R7, multiple registers, then you can easily delimit the registers with this dash. So if you specify R1 minus or dash R6, what does it actually mean is it will push R1, then R2, then R3, then R4, then R5 and then R6. So you can just minimize the code understanding of the code by delimiting with a dash. So what we are going to do now? We are going to create a program where we will just use all the push and pop instructions, and I will just demonstrate you how the stack looks like in a program. What is stored in the base address register, is stack pointer register, how does the stack pointer register fluctuates within a stack instruction execution. So let's create a program and debug it. So let's move to our computer screen. So what I have done is created a simple file named as stackinstructions.s where I have just filled R0, 1 and 2 with the 32-bit values via the help of move W and move D instructions. If you don't know what are all these move W and move T instructions, please refer to the previous video where I have described all the variations that we can use with the move instructions. So please refer to the previous video, you will learn a lot. So what I am actually doing in this program is simply pushing some registers and popping some registers, which you will see what is happening actually in the debugger session. So what I am using here is a debugger known as GDB to just debug our program, and another utility known as chemoarm because I am executing ARM instructions in Intel machine, which is not technically possible because you cannot execute ARM instructions on Intel or AMD machines. So with the help of this utility, I can do so. If you want to know how to download all these utilities, please refer to the fourth video of this playlist. You will just download all the utilities required for this entire playlist, required for you to just execute ARM instructions on Intel machine. So what I am doing is linking the file with an external library stored in a user library ARM Linux GNU ABI HF, creating a debugger server with the tag G on the port 1234 of the program stack instructions. After executing or pressing enter, what I am actually doing is creating a debugger server on 1234 of this process, which I will debug via another terminal remotely. So how can I access the debugger server of this another terminal into this is by specifying target remote localhost 1234. So after pressing enter, I have just gained the access of the debugger server remotely of any other terminal. So what I am doing in the next 6 instructions is just loading the register, so I will just skip that fast enough. So let me just show you the register values of R1, R2 and R0 is the 1, 2, 3, 4, 5, 6, 7, 8, 4 times 1, 4 times 2, 4 times 3, 4 times 4. So which I have just stored with the help of move W and move T instructions. So let me just show you the top of the stack or the stack pointer, which is actually 4080080, which you can easily see in the JEF utility, JEF extension of the debugger, which is actually the same. So in the normal GDB you will not get these enough information, so you have to install GDB JEF to get all these information separately. It might help you a lot. So after executing the first push instruction, what we are doing is pushing R0. So make sure you just watch the value of R0, which is 1, 2, 3, 4, 5, 6, 7, 8. And after pressing enter or stepping instructions ahead, what I have pushed to the top of the stack is the exact same value of the R0 register, which is top of the stack, and the top of the stack is incremented. The top of the stack is decremented by a 4. So which means the stack is growing from higher memory address towards the lower memory address. Stepping one instruction ahead, what we are pushing is the value of the R1 register, which is 1111 and 2222. After pressing enter, let me just view the top of the stack is the 1111 and 2222, and the stack pointer is decremented again by a 4. So what I am doing now is executing another stack instruction, the pop instruction, and what we are popping from the top of the stack is the value 11 and 22 into the R3 register. So just view the value of R3, it is 0, but after specifying or stepping one instruction ahead, the value of R3 will be exactly the same as the R1 register, and stepping one instruction ahead, the R4 will store the value of R0 register. So at this point, what we can easily see, the stack pointer also fluctuates, also decrements or came into the exact location from where we started, because we have executed 2 push and 2 pop instructions. So stack just ends up at the same place where we have started with. So at this instruction, what we are doing is specifying a set of registers to be able to push on the stack. And if I just view the values of R0, R1 and R2, it is 1, 2, 3, 4, 5, 6, 7, 8, 1, 1, 1 and 2, 2, 2 and 3, 3, 3, 4, 4, 4. So after specifying or stepping instructions ahead, what I have done is pushed R2 first, R1 second, and at the very end the R0 register's value has been pushed, and the top of the stack will point to the value exactly to the R0 register's value. Next instruction is a pop instructions, where we are popping the top of the stack into the R5. then the subsequent values of the stack into the R6 and R7 registers. So let me just view you the values of R5, R6 and R7. It is 0 0 0, all 3 0. After stepping one instruction ahead, the stack will be empty again, and the R5, R6, R7 will be filled with the exact value of the R1, R2 and R3. The stack is came back to its original state. Values are again in the registers the same as R1, R2, R0, R1 and R2. So what I have done in the program is specified R0 to R5 with a delimited character dash. So in the debugger session, what it is actually meant is it is just decoded into the instructions or the registers automatically. So what I am pushing is pushing all the registers from R0 to R7 on the stack. So all the data of the registers stored in the registers are just pushed on the stack, and subsequently the registers values are popped into the registers respectively. So this is how a stack works. The stack pointer also just came to its original state because we have pushed 7 registers, or we can say 8 registers, and popped into 1, 2, 3, 4, 5, 6, 7, 8 registers. So doing the exact number of registers of push and doing exact the same number of registers with a pop results in a same state from where the stack pointer or top of the stack starts from. So what our program is actually doing is just gracefully exiting the process, and that's all for this video. If you have any query related to this video, you can just simply ask in the comment section. All of your queries will be resolved within an hour or two. If you have any if you want to download all the slides used in this video, you can just refer to the description. I have provided you the link. Also the codes are provided too. You can follow me on my Twitter and GitHub as well. That's all for this video. Meet you in the next one.